This is the logistic regression video on assessing model fit. For continuous outcomes, you might recall that the measure of fit used as input into the partial F test, namely the model sum of squares, was closely related to the model R-squared, which quantifies how well the model fits on an absolute scale. In logistic regression, there are at least two analogs for the R-squared. One of these is called the generalized R-squared statistic. The formula is on the slide. And although it might not be immediately apparent, for continuous outcomes this formula really does reduce to the R-squared with which you're already familiar. Technically, the generalized R-squared statistic doesn't retain the interpretation of percent variation, the outcome that explains by the model, but it doesn't do any harm to imagine that it's doing something similar. For some data sets, it's impossible for the generalized R-squared statistic to reach 1. In that case, some statisticians prefer to use a version that's rescaled by dividing by its maximum possible value. The idea is the same. An alternative to the generalized R-squared statistic is the C statistic. The C statistic will be large when the logistic regression model successfully distinguishes between patients at high and low risk of outcome. To see the connection between this idea and the description of the C statistic on the slide, imagine that you're going to compare every pair of patients. What you'd like to see is that the model predicts a higher probability of outcome for those patients that do actually have the outcome, and a lower probability of outcome for those patients who actually don't. Patients with identical outcomes don't really contribute to this calculation. One thing that's important to realize is that the C statistic doesn't measure calibration. In other words, the C statistic doesn't start with patients for whom the model estimates will have a 20% chance of having the outcome, and then proceed to check whether 20% actually do. All the C statistic does is verify that the model correctly distinguishes between patients at relatively high and low risks of outcome. The statistical term for what the C statistic is measuring is concordance. This slide illustrates the nuts and bolts of how the C statistic works. Patients 2 and 3 are concordant and would contribute towards a high value of the C statistic. For this statistic, some statisticians use benchmarks of 0.7 as representing fair concordance and 0.75 as representing good concordance. This slide illustrates the difference between concordance and calibration. The predictions are in the correct order, illustrating good concordance, but aren't well calibrated. Strangely enough, it turns out the C statistic also represents the area under the receiver operating characteristics curve, which is most commonly fit when the predictor variable is a continuously scaled diagnostic test, and the outcome is the presence of disease. Just in case you're unfamiliar with ROC curves, to create one, select the threshold value for the continuous diagnostic test. For all patients with values below this threshold level, classify into disease present and disease absent. Do the same for patients with values above the cut point. You now have a 2x2 table and can calculate sensitivity and specificity in the usual way. The important thing to note is although the total number of patients with disease doesn't change, what does happen when you change the cutoff value is that the distribution of test results might. In other words, although the sum of A and C remains constant, A and C can change. To create the ROC curve, select a cut point for the continuous diagnostic test. Plot sensitivity as obtained from the 2x2 table in the previous slide on the x-axis and 1 minus specificity on the y-axis. Now change the threshold value, repeat the procedure, and plot another data point. Doing this for a large number of data points forms the ROC curve. The closer the curve is to the upper left-hand corner of the graph, the better. Moreover, the threshold level associated with the upper left-most point is the optimal value for using the cutoff for the diagnostic test. Here's a picture. The best cut point is at the far left-hand corner, and the C statistic is the area under the ROC curve.